We all learned that classic rule in physics class. Energy can't be created or destroyed. But think about it for a second. If that's really true, then why does a bouncing ball eventually stop bouncing? Why does anything eventually stop moving? Today, we're going to dig into the real-world physics that seems to totally break that fundamental rule.
So, is energy really always conserved? Well, yeah, kind of. The thing is, while it's fundamentally true for the entire universe as a whole, when we zoom in on the mechanical energy of a system right in front of us, like that bouncing ball, the story gets way more complicated and honestly, a lot more interesting.
All right, so to really get to the bottom of this, we first have to talk about work. Now, in everyday life, work is, your job or mowing the lawn. It's just effort. But in physics, it's something way more specific. It's all about applying a force to actually move something.
So how do physicists nail this down? Well, they use this formula. And I know it might look a little intimidating with all the letters and symbols, but all it's really asking is a simple question. How much of your push is actually helping to move the object in the direction it's going? That's the whole game right there.
Okay, so what's up with that cosine theta part? What's it even doing there? Well, think of it like this. It's just a way to measure alignment. It's asking, how much are your push and the object's movement in sync? If you push a box straight forward, boom, you're perfectly aligned. 100% of your force is doing useful work. But if you push down on it at an angle, well, only part of that force is actually moving it forward. The cosine is just a handy-dandy math tool that figures out exactly how much of your push is the useful part.
Okay, so before we dive back into the messy real world, let's take a quick trip to a perfect physics world. The kind you see in textbooks. A world with zero friction, zero air resistance, none of that annoying stuff. In this perfect little bubble, mechanical energy is neatly conserved, all thanks to a very special kind of force.
And these are called conservative forces. The classic example, the one everyone uses, is gravity. Think about it. The work gravity does on you when you go down a flight of stairs is exactly the same as if you slid down a ramp to the same spot. Gravity doesn't care about the journey you took, the path you followed. All it cares about is where you started and where you ended up.
And this pendulum? It's the perfect poster child for this idea. In our perfect little physics world, this thing would just swing forever. At the very top of its swing, it just hangs there for a split second, holding all its energy as potential energy. Then, as it falls, that potential energy beautifully transforms into the energy of motion, kinetic energy, until it's going at its fastest right at the bottom. And that speed is what carries it all the way back up the other side, turning that kinetic energy right back into potential. It's just a perfect, endless dance between the two.
A really great way to think about this whole thing is with a money metaphor. Let's call it the energy budget. Your total mechanical energy is like the total amount of money you have in the bank. Your potential energy, that's your savings account, stored away. And your kinetic energy is your checking account, ready to be spent on motion. So these conservative forces, like gravity, all they do is transfer funds between your savings and checking. The total amount of money you have never, ever changes.
But, as we all know, that's not how things work, right? Pendulums don't swing forever. So, let's pop that perfect little bubble and come back to the real world, where things get messy and this perfect system starts to fall apart.
And this brings us right back to our original question. If energy can't actually be destroyed, then where in the world does the energy of a bouncing ball go? I mean, it really seems like it just vanishes into thin air. But it's not gone. It's just been hijacked and transformed by a completely different kind of force.
And here's our culprit, the non-conservative forces. Friction is the #1 bad guy here. See, the work done by friction absolutely depends on the path you take. It cares a lot about the journey. Pushing a heavy box 5 meters across a gritty floor takes way more work than pushing it just 2 meters. And all that extra work, it's basically stealing mechanical energy from the system and turning it into something else, usually just heat.
This table really lays it all out for us. On one side, you've got your conservative forces. These are the clean, the neat and tidy forces like gravity that just swap energy between potential and kinetic. But on the other side, you've got the messy, real-world forces, the non-conservative ones like friction and air resistance. These are the ones that always seem to be siphoning energy out of the system. These are the guys we have to keep track of.
So let's go back to our energy budget metaphor for a second. If conservative forces are just moving money between your accounts, then non-conservative forces are like an unavoidable, super annoying bank service fee. Every single time you make a transaction, every single time the object moves, friction and air resistance take a little cut. And that fee gets paid out as thermal energy or heat,
which slowly but surely drains your account of all its useful mechanical energy.
Okay, so how on earth do we actually account for this seemingly lost energy? We need a bigger, better tool. We need to expand on the basic work-energy theorem. The good news is, there's an equation that perfectly brings both the ideal world and the real world together under one roof.
All right, let's start with the basics. The simple work-energy theorem is a great place to begin. All it says is that the total or net work you do on an object equals the change in its kinetic energy, its energy of motion. So if you do positive work on it, it speeds up. If you do negative work like friction does, it slows down. Simple enough, right? But now, let's add a layer of detail. We can take that net work and just split it into its two parts. The work being done by our clean, conservative forces, and the work being done by our messy, non-conservative forces. Both of them, added together, are what cause that change in kinetic energy. And with just one little bit of algebraic shuffling, we get this. This right here is the master equation. This is the key to everything. It tells us that the work done by those messy, non-conservative forces, WNC, isn't just some random energy leak. No way. It is exactly equal to the total change in the system's mechanical energy. That's the change in kinetic plus the change in potential. The energy isn't lost. This equation lets us track it down and tells us precisely where every last bit of it went. Okay, let's put this equation to work. Look at this cyclist. As she coasts up the ramp, two things are happening. She's losing kinetic energy, right? She's slowing down. And she's gaining potential energy because she's getting higher. Well, the work being done on her by friction and air resistance is precisely equal to the sum of those two energy changes. It's like a perfect energy audit. Nothing is unaccounted for. So, we figured out how to account for the amount of work being done. We can track every joule. But there's one more piece to the puzzle. What about how fast that work gets done? And that, my friends, brings us to our final big idea: power.
Power is actually super simple. It's just the rate at which you do work. It's not just how much work you do, but how fast you do it. We measure it in watts, which is really just joules per second. I mean, think about it. Doing 100 joules of work in 1 second is way more powerful than doing that same 100 joules over the course of a whole minute.
And here's where it gets really cool, especially if you're into things like engines. Check this out. If we start with power equals work divided by time, and we swap in the formula for work, we get force times distance all over time. And what's distance divided by time? Well, that's just velocity. So another way to calculate power is simply force times velocity. This is a super handy shortcut, especially when you're talking about anything with a motor.
Okay, pop quiz. A person and a robot both lift a 50-kilogram crate 2 meters off the ground. Now, technically, they've done the exact same amount of work, right? Same force, same distance. But the robot does it in 1 second flat. So who's more powerful? Of course, it's the robot. It's not even close. It generates way more power because it did the exact same work in just a fraction of the time.
So, let's bring it all home. What are the big takeaways here? First, work in physics isn't about sweating. It's about a force acting over a distance. Second, that idea of perfect energy conservation, that's really only for ideal friction-free systems. In the real world, non-conservative forces like friction are always converting that useful mechanical energy into other stuff, like heat. And finally, and this is the big one, we have our universal law, WNC equals delta KE plus delta PE, that lets us perfectly account for all those energy changes. Nothing is ever truly lost. You just have to know where to look.
And we'll leave you with this final, really important thought. The whole reason physicists are so careful about these distinctions is because a true conservation law has to be true for everybody, everywhere, no matter how they're moving. And the total energy of the entire universe really is conserved. Understanding the role of work and friction and all these messy forces, well, that's what lets us balance the books on a small scale so we can finally see that bigger, perfect, universal conservation that's always at play. Thanks for joining me.